Hello, my name is Jackson and I am a PhD candidate, member of a research group on software engineering from Federal University of Paraná, Brazil. I am supervised by Professor Silvia Regina Virgili. In this video, I am going to present our paper entitled Multi-Armed Bandit Test Case Prioritization in Continuous Integration Environments, a Trade-off Analysis. The software development is growing fast, and along with it, the adoption of the agile development process that allows a continuous evolution of the software with fast deliveries. A practice adopting agile development is the use of CI environments. These environments allow the integration of frequent software changes by automating the process of building, testing, and notifying test results, thus allowing a rapid and advanced evolution. In continuous integration environment, regression testing is fundamental. Due to frequent changes and integration, test cases need to be executed multiple times a day. In the literature, there are many techniques for reducing regression test costs. Among them, we highlight the prioritization of test cases, that aims to reward the test case according to some objective, for example, to detect faults more quickly. The advantage of this technique over others is that it considers all test cases, not just a select or minimized subset. However, most prioritization techniques do not adequately deal with the test case volatility in an agile environment. That is, they do not deal properly with the fact that test cases are added and removed or discontinued between commits. In addition, there are also restrictions in the CI environment such as resource and time constraints. To overcome such limitations, learning approaches based on historical failure data have been explored. This approach learns with past prioritizations, usually guided by a rewarding function and deals properly with the test case volatility. In the literature, a learning approach that stands out is COLEMAN, a multi-armed bandit approach. Multi-armed bandit is a kind of reinforcement learning that works with a class of sequential decision problems that are intensively studied to solve the dilemma of exploration and exploitation. A bandit can be thought of a player plays in front of k gambling machines, and each machine has its own reward distribution. At each time, the player selects an arm and obtains a reward. The objective is to control the choice to maximize the accumulated total rewards. To this end, a policy is the strategy that chooses at each time the next arm to pull based on previously observed rewards and decisions. Often, developing teams integrate their codes, and for that, a version control system is used, which is monitored by a CI server. When a change occurs, the server clones this code, builds and runs the testing process. When the process is finished, a report with feedback about the results is generated by the CI server and interested parties are notified. COLEMAN acts after a successful build. In the test phase, the approach prioritizes the test case set available to be used during the test case execution. Then, according to the performance of its previous prioritization, the policy receives a reward. Based on rewards provided by a reward function, the map policy adapts its experience for future actions. COLEMAN adequately addresses CI particularities such as test case volatility and test budget, and it can be considered the state-of-the-art approach for test case prioritization in continuous integration environments. Reported results show that COLEMAN overcomes similar approaches in terms of early fault detection and execution time. Despite these promising results and advances, there is no study comparing COLEMAN with near-optimal solutions such as the ones generated by a search-based approach. Given the fact that search-based approaches consume much time to execute and are not suitable to the CI environment, then a question that arises is, how far are the solutions produced by a learning approach like COLEMAN from the solutions produced by an optimization approach? This work aims at answering this question. In this study, we aim to compare COLEMAN with near-optimal solutions generated by a genetic algorithm. It's essential to highlight that the test results are already known a priori, that is, we design a genetic algorithm, GA, to find the near-optimal order for a test case set available in each commit under different test budgets. This allows us to observe the difficulty behind to the problem even knowing the test results. Concerning the genetic algorithm settings, each individual in the population represents a possible prioritization for the test case set available in a commit. To represent an individual in the population, we use an integer encoding, and the gene represents the test case priority, that is, the execution order in the prioritization test case set. Thus, the genetic algorithm is designed as a permutation problem. We use the NAPFD metric as a fitness function to guide our genetic algorithm in the search space. This is a common metric used to evaluate a prioritized test case set under time constraints concerning failure detection effectiveness when not all of them are executed. As we desire the best prioritization, the problem is treated as a maximization problem. We evaluate our study guided by the following research question. How are the solutions generated by COLEMAN compared to the near-optimal solutions found by a genetic algorithm? We used three metrics to evaluate the study. NAPFD provides the quality of the prioritization concerning early fault detection and better fits the CI time constraints. Prioritization time considers the time taken by the approach to perform the prioritization. RMSE evaluates the difference between the predicted and the observed values. We use RMSE to compute the difference between the NAPFD values in each community obtained by COLEMAN and the near-optimal values found by DGA. We compared the results using Kurzweil-Wallis statistical test and Vargan-Delaunay's for effect size. The experiment considered three time budgets concerning respectively 10, 15, and 8% of the time available to execute the tests. For COLEMAN, we used the fitness rate rank based on Multi-Armed Bandit FRR policy that provides a slide window to observe the historical test data, and we observed the last 100 commits. This policy obtained the best performance against other policies in previous work. The rewarding functions used were RNFail and time ranked. RNFail is based on the number of failures associated with a test case, and this function captures the ability of a test case to produce failures. Time ranked evaluates if the failing test cases are ranked in the first positions in the prioritized test set and penalized by early scheduling the test cases that do not fail and persist the failing ones. We used 7 large-scale real-world software systems. The results were obtained from 13 independent executions for each algorithm in each time budget, reward function, and system. A complete information about characteristics of the systems, the source code of the genetic algorithm, additional analysis, and results are available in our supplementary material. To answer the research question, we use this table that shows the NAPFD, RMSE, and prioritization time values. In the first column is the system under test. The values are separated by metric, approach, and time budget. COLEMAN is represented by the reward functions used. The best values are highlighted in bold, and values that are statistically equivalent to the best ones have their corresponding cells painted in light gray. Different symbols are used to indicate the effect size magnitude concerning the best values. In summary, regarding NAPFD values, GA outperforms COLEMAN in all systems in all time budgets with a large magnitude and statistical difference. Concerning RMSE values, time rank has the best values, in most cases with statistical difference. And regarding prioritization time, we observe in all systems a relevant difference between genetic algorithm and COLEMAN execution time, mainly in the Druid system. As expected, COLEMAN is much faster than GA. However, how does such a gain in time impacting the NAPFD values? Does more time imply better prioritization? Next, we investigate such a trade-off by analyzing NAPFD and RMSE. Regarding NAPFD value, GA has the best performance. This is expected, as mentioned before. DGA previously knows the testing result and is required only to find an approximation from the optimal prioritization. In this way, the results found by GA are used as a baseline to observe how distant the prioritization proposed by COLEMAN is. Considering this aspect, in some cases, the NAPFD values reported by GA are close to the ones obtained by COLEMAN. They suggested COLEMAN proposed near-optimal solutions. Besides, time rank performs a bit better than RNFail. Analyze the correlation about NAPFD and systems characteristics, we observe that deep learning for GA has a high average of failing cycles. However, only this does not help COLEMAN to provide a good prioritization. Because of this, we analyzed other relevant characteristics that may impact in the prioritization, such as test case volatility. In such a system, we observed a high test case volatility, mainly in the failing test case, consequently, hindered the prioritization. Such behavior also impacted the GA performance. We observed the highest difference between COLEMAN and GA in the Druid system. This system has some particularities. 1. It has a high average of failing cycles, what would benefit a failure history approach, but it has 2 peaks of failures which increase the average of failing cycles. 2. This system has a large test case set, in which many failures are distributed in many test cases, and 3. Few number of CI cycles. These particularities negatively affect COLEMAN to find good prioritization, and GA, which required a lot of time during optimization. COLEMAN and GA obtained the worst NAPFD values in the IOF raw systems. This system encompasses a high test case volatility coupled with a great number of failures distributed over many test cases. The high test case volatility may be associated with a price limit strategy because the test cases reappear in some cycles. Consequently, this hampers to find a reasonable solution for our problem. The NAPFD metric gives us a quantitative notion about prioritization quality. However, to effectively calculate how far the COLEMAN solutions are from the GA near-optimal solutions, we use the RMSE values. Time rank has the best values in most cases with statistical difference. RMSE outperforms time rank in only one case. Besides, we observe that time rank is better in the hard case, deeper learning for J and Druid. This metric is adequate to evaluate an approach effectively. For instance, both algorithms report small NAPFD values for the IOF raw system, but this occurs due to its characteristics that challenge in writing finding reasonable solutions. In these systems, all RMSE values are around 0.2, which represent solutions close to the optimal. The worst RMSE values are for the system Druid in the time budget of 10%. As mentioned before, the bad performance is associated with the characteristics of the system and with the consistency of the historical data. In order to provide a better representation of the RMSE values, we defined an RMSE scale of magnitude. Such a scale shows the distance from the near-optimal solutions, where the very near category represents an approximated optimal performance, and the very far category represents solutions that are far away from the to be useful and considered reasonable. The reasonable category represents the minimal acceptable performance. Based on the RMSE scale of magnitude, we identified that time rank obtains very near optimal solutions in 13 cases out of 21, and 7 cases in the category near, while RMSE respectively in 8 and 10 cases, and 1 case in the reasonable category. Both reward functions have 1 case in the very far category, in the Druid systems for the time budget of 10%. The best solutions found by both reward functions are for the time budget of 8%. Considering the analysis reported, we can conclude that the prioritization time had no significant negative impact in the COLEMAN solutions. The time spent by COLEMAN to prioritize is negligible. This metric also helped to observe the difficulty inherent to our problem taught the values reported by the genetic algorithm. This algorithm in some systems spend a lot of time to prioritize. Finally, COLEMAN provides solutions that are near or very near to genetic algorithm solutions in 90% of the cases, considering all systems, budgets, and both reward functions. Now we discuss the main findings highlighting some research directions to COLEMAN in learning approaches. COLEMAN performance is better in the presence of a less restrictive budget, that is, in this scenario the solutions are very near to the optimal. As COLEMAN is based on the failure history, a greater quantity of cycles and few peaks of failure seems to make the prioritization easy. Some factors that hamper the prioritization: a high volatility of failed test case, a large test case set in which many failures are distributed in many test cases, and a small number of CI cycles makes the learning hard, mainly in the presence of restrictive budgets. To mitigate the factor concerning few cycles, a way is to reduce the slide window size used by COLEMAN. This may get better results. Another research direction to be investigated is the use of a hybrid approach to mitigate the limitation of starting without learning. Time rank performs a bit better than RMSE. A great difference is observed in the less restrictive budget. It seems that the use of other information besides the ability of a test case to produce failures can improve the performance. Maybe other reward functions should be explored, such as one that considers the test case execution time. As in summary, this work evaluated the trade-off of COLEMAN, a multi-armed bandit approach for test case prioritization in CI environments. The solutions produced were compared to near-optimal solutions found by a genetic algorithm. COLEMAN yields near-optimal solutions with negligible time, a high test case volatility, mainly in failing test cases, associated with a high number of failures distributed over many test cases hampers inadequate prioritization. Such a difficulty makes the problem hard, even for genetic algorithms that took a lot of time to execute. The results presented here can serve as guides to evaluate future approaches in the test case prioritization in continuous integration context. Furthermore, the characteristics of the systems can be used by the researchers to redirect their research to better results. As future work, we intend to use our study as a base to derive and evaluate new approaches. In this sense, the use of other evaluation measures as a fitness function to the genetic algorithm. Besides, other systems with a greater number of failures and test cases should be used to evaluate scalability. I hope you enjoyed this presentation. Thank you.